So for this problem, what they're asking is for you to draw on the graph these step functions. This step function you can see is only consisting of one component, whereas you can have step functions that consist of multiple components. The step functions are things that you would put into the control system to see how the plant will act over a certain time period. In certain sections of the plant, you could see how the signals will be reacting depending upon these different type of inputs. So for the first one, when it says t minus 5, the t minus 5 is the place where you would need to begin the graph. So at t minus 5, that would be this location right here. And you would just draw a consistent line out. So that means that the signal does not start until you get to 5 seconds. And then after 5 seconds, it will be a consistent 1 throughout. The next one is a string of components, a string of step functions that would go into your control system starting at 0, because there is no t minus any type of number. So starting at 0, it would look something like this. You'd keep going until you got to t minus 3. At t minus 3, you'd step up 2 from where you're at, not just go to 2. So it's all relative, so it's from the position that you currently were. And then you continue on to where it says 8. And then because of the negative sign right here, -1, you would go down 1 from where you're at and continue the rest of the way. So for this problem, this is a transfer function, and you need to be able to break this up into components to be able to analyze to bring into the time domain. So you can tell this is a Laplace transform by the s's and the f, the capital F that you see here. So breaking this up into components, it would look something like this. It's called partial fraction decomposition. So you have your s plus 1 plus b over s plus 2 plus c over s plus 3. So the goal is to be able to find a, b, and c. And if you can find a, b, and c, it's a lot easier to convert that back into the time domain. So a nice trick that I like to do, how a lot of people are taught how to do it, is take the denominator, multiply it on the other side, and take away and try to solve one component at a time. What I like to do is I like to think of it like this, where you're crossing out this first denominator, and all of A would be considered as F plus S over the remaining the remaining components in the denominator. And where you took out S plus 1, you think of the number that would make this 0 if you replaced S, and that would be -1. So you replace these S's with -1, and you'll get 2. So if S equaled -1. So following this logic, you would do this for each one of these denominators. So B would equal 5 plus S over S plus 1 and S plus 3, where S in this case will be -2 because that's what it will take to make this 0. So when you set that to -2, you'll get -3. So if you follow this trend for the last one, you'll get C is equal to 1. So taking these components, your overall function in the time domain would look something like this. So from this, you want to be able to convert each one into the time domain. It's a lot easier to do this now because you have broken this up into components. So what I just added was a table of Laplace transforms, and this will allow us to convert it back into the time domain. This is what is commonly used. So what you do is you need to find the pattern of each one of these components. So the thing that looks closest to each one of these is this equation here. The 1 over s minus a. So as long as that is consisting of that form, you can convert it into e to the a t. So this would look something like this, where now this is a 2, so this can be considered as, you can factor this out. This would be 2 over 1 over s plus 1. You can think of it like that. So because the 2 would be on the bottom, something like this, we have 1 s plus 1. So now this matches this form. Your a would be 1, but because it needs to be a negative sign, you'd make this into a negative when you put it where the a is. So this would be 2e to the negative t. So that would turn into that, and that would turn into that. So this would be added, or rather subtracted, with 3 that you factored out to the e, or times e to the negative 2t. And the last one would be e to the negative 3t, because there's nothing to bring down. So this is what it would look like if you made it into the time domain. And from here you can actually analyze things like taking t and putting it to infinity, so you can tell what the system will do once the system has kind of settled out, and see what the signal is over a long period of time. But there's tricks to be able to do this while staying into the Laplace domain, while staying into the frequency domain that I'll explain next. So this question is wondering how you will be able to get in the time domain, because this is a small f, what is the signal as time approaches infinity? And right here it shows the Laplace domain. So if you wanted to, you can convert it to the time domain and do exactly what we did in the last problem, but that will take, as you saw, it takes a little bit of time to do. Ideally, what you'd want to do is be able to do that, but still stay in the Laplace domain, and there's a trick in how to do that. So this is what you would do. So this is what you would be doing to actually get f infinity. And there's a proof behind how this works. I don't want to go into it here, but on the lecture notes that I posted on Slack, you can see, if you're really interested in why this works the way that it does, there's proofs to back it up. But if you ever wanted to find out how a signal will react over a long period of time but still stay into the frequency domain, you can use this technique. So this system, or this equation, would end up looking something like this. S's would cancel out. You'd be left with so looking at this, if you took the S's and made them 0, like what you see I'm doing here, this would cancel out, this would cancel out, this would cancel out, and you'd be left with 2 over 3. For this next problem, the same exact rule applies, except you would do the opposite of f of 0. You do f of infinity. So if you wanted to do that, this is what it would look like. You would think of this as the limit as s approaches infinity. So these would cancel out, these would cancel out, and so and this also would cancel out, and what you're left with is 2. The reason why these would cancel out is because if you make this infinity, those would go away. The 5s and 2s would also cancel out. And then the 6 would be a smaller, insignificant number because of the infinity. And so this would also cancel out. And so you'd be left with just 2. So this one is a good one in that this is a second order transfer function. And what they're asking you to do is be able to find out the undamped natural frequency from this transfer function, as well as the critical damping ratio and then the gain. So you know that there's a gain here, so the overall system that you're trying to model after would look something like this. So let's start with what we know. We know that omega squared and omega squared, they both have to be the same number, and 4 can't change here. So we know that omega squared has to be 4 because of what's right here. So let's start off with that. So omega squared is equal to 4. You square root both sides, you'll get omega is equal to 2. Omega can't be a negative number, so we know that it's positive. So after you found omega, let's find k. So you know k omega squared, which is on top, needs to be equal to 1. And you already know omega squared is 4. So in this case, k would be equal to 1 over 4. So for zeta, we would do somewhat the same thing. So you know that there's a 3s right here. So we take 2 zeta omega s is equal to 3. And from that, we know that zeta will be equal to 3 over 2 omega. Sorry, you don't include the s here. So this would not be included. So it'd just be 2 zeta omega is equal to 3. The reason why you don't include s because that's part of the form here. You need the s. So the 3 would just be the 2 zeta omega. So you have 2 zeta omega is equal to 3. So zeta would be 3 over 2 omega, which is equal to 3 over 4. So what this, let's recap real quick. What zeta means is the damping ratio that you have to your system. So if I were to draw this out on a curve, you might have something that looks like this, where this is where your system settles. You might have some overshoot, some slight overshoot. So if this was a 1, you'd probably have something that looks like this, or 1.1 or anything that's over 1, that's a critically damped system, and you'll have a smoother curve when going there. And omega is your frequency, and if you know your resonance frequency of your system, you don't want this frequency to match the resonance frequency. So it would look something like this, where your resonance frequency, so this is the resonance frequency divided by 2 is still going to be bigger than your omega. So you want your omega to be a relatively smaller number than your resonance frequency. So for this next problem, this is a first order transfer function denoted by just this one s. So the form of this is k over t ts plus 1. So to get that in this form, all you need to do is divide the a right here by a, divide b by a, and divide 1 over a, so that you can get the necessary 1 here to make this into the model. So you have b over a over 1 over a plus 1. So here, the b over a is your gain of the system, and your 1 over a, sorry, I forgot an s, the 1 over a is your time constant. And to recap this, what it would look on the curve is something like this. Where you'll have the signal go up, your gain would be where it goes up to, so your end destination, and the time would be 63.3% of the system going to the max point. So for this one, they want you to know how the time constants of the brushed DC motor relate to each other between the electrical contribution and the mechanical contribution. So like we did before, this is a first order system because of this s. If you want to know your time constant, you just follow this form. So to get that into this form, you need to divide by RA for each one, and you'll get something like this. You have 1 over RA over LA over RA S plus 1. So your time constant here is LA over RA. So time constant of electrical. And they give you LA and RA. So in this case, if you divide those two numbers, you would get 0.000108 seconds. So for the mechanical contribution, you do the same exact thing where you divide by BM. So for the mechanical, you would have JM over BM, and you would get 1.11 seconds. So they want to show you how much more the mechanical time constant is from the electrical time constant. So that would just be the time of mechanical over the time of electrical. You get 10,278 times bigger than electrical. And the reason why they want to show you the significance is because if you can understand that, you know that the time constant of the electrical contribution can be shown to be insignificant, and you don't have to include it into your overall model. And you'd like to make these simplifications if possible because it makes the overall model and analyzing it a lot easier. So for this one, I'm going to draw the block diagram for the brushed DC motor. So, like I was showing you before, the time constant was insignificant compared to the mechanical time constant. So, in knowing that, we can confidently cross out the time component that's consisting of S because we know that it won't affect the overall system. So in doing so, you're left with just 1 over RA. For block diagrams, when they're in series like this, you would just multiply them together. So your overall system would look something like this. So now that you've reduced your system into this, the next step would be to reduce it even further. And if you have a system that it consists of a feedback loop like this is how you would solve it mathematically. So what I did here was I took this transfer function, and this is the exact same thing that's in the numerator. However, you take this number, and it's if you have a feedback system where this is a negative sign, this will be 1 plus the same exact thing, whatever this was on the bottom here. So you can see that this transfer function that was in this block is the same exact thing that's right here. And the only thing that I did with it is I multiplied it by KB as I was going back around in the feedback loop. This will be a positive or negative depending on if this is a negative or positive. So if this is a negative, this will be a positive. If this is a positive, this will be a negative. So in this case, you have something that looks like this. How I like to think of it is I like taking the denominator of this guy here and bringing it down 1 level. So this would be in this place, and then you would factor in it to this number, getting rid of this bottom line right here, just leaving the KA and KB. So it would look something like this. So this is your overall transfer function. And this would be considered your plant. So because this is a first order transfer function, as you can see by just this one S, you can analyze it like you would a normal first order transfer function. So you know that the form is K over TS plus 1, and that needs to take this form. So that means this number right here needs to be divided by Ka and RaJm. So that would look like this. So what these values, if you look on the top, you'll see that the Ka, Ra, and Bm and Kb are all given. you'd end up getting 34.59 for your gain, and for the time constant, it would be 0.023 seconds.